All right, so first of all, I'll tell you a little bit about Hubbell and who we are here. So Hubbell has been around for over 100 years. We were founded in 1920 as the electric heater company. And the company was purchased by Harvey Hubbell in 1926, and that's how we got our name. So there's still a distributor down the street called Hubbell that distributes electrical products. That's the leftover from Harvey Hubbell. And then the company was taken private in 1931 by two families. And it's been a family-owned business. We're on the third generation of those families that initially purchased the company in 1931. So we are a small family-owned business. Everything that we do is made in the United States. So we're Buy American compliant, we're Buy America compliant on all of our products. And we manufacture in Connecticut, Massachusetts, and California. So our focus is really on commercial water heating needs. We do some residential stuff, but instead of some companies who kind of take residential stuff and push it out into the commercial space, we take commercial stuff and push it down to the residential. So we're focused on really the needs for the commercial market and long-lasting, high-performing water heaters for that environment. Quick overview of the line of water heaters that we offer. So we offer a full line of water heaters. The inputs are going to be electric, gas, steam. We do indirects, heat pumps, which is what we're going to focus on today. We do basic storage tanks. We do storage type heaters, instantaneous heaters, point of use. And we focus a lot of times on applications that are specialized. So things like pure water, explosion resistant, circulation heaters, booster heaters. We do custom water heating skids, pretty much whatever you guys want, with various vessel materials, various size tanks. So any questions that you guys ever have about, can we do something, if it's custom for a job or whatever, that's kind of our specialty as a company here, okay? So when we talk about heat pumps, I'm going to explain briefly how they work. There's a lot more that goes on inside these units than what I'm going to talk about here, but it's important to understand how, have a basic understanding of how these units work in order to understand the limitations and what they can actually do. So a heat pump uses the exact same cycle as an air conditioner or a chiller. It's called a Rankine cycle. And so if we start here to the left of the compressor in our loop, this loop is filled with a fluid called a refrigerant. And the refrigerant is selected based off of the properties of it, what temperatures you're trying to get out of it, what temperatures you can provide it or whatever. And it's, you know, there are different types of refrigerants out there and whatnot, but at this point, we're just going to look at it as a liquid. And so when we run it through the compressor, we're going to have a gas actually on the left side of the compressor. We're going to run it through there, and it's going to raise the pressure of that gas, and it's going to raise the temperature as well. So we then take this gas and we put it through a heat exchanger, which is called the condenser. And the idea of the condenser is we want to take this gas and make it into a liquid. And what we get out is heat. We get hot water out of it in the case of a heat pump. So what we've done after it runs through the condenser is we've dropped the temperature. Ideally, the pressure is exactly the same. It drops a little bit because there's pressure drops in there, but we end up with a liquid. Now the liquid is next run through an orifice, which is what it sounds like. It's a small hole. It's actually adjustable depending on temperatures and stuff within the system, but we'll just look at it as a small hole. And it allows a different pressure on the right side of it versus the left side. And so when you release, when you go from this liquid to a mixed phase, a liquid and a gas, it's going to cool it. You're going to drop the pressure, but it's also going to cool it. Think of a spray can. When you spray paint, you're going to feel that can get very cold when you're out there tagging stuff, and that's what happens here as well. So now we have cold in the system. We have to take cold out. So this would typically be where the air conditioner would. This is what you want with an air conditioner. A chiller is cold. We call this section the evaporator. Okay. And what we want to do is take this mixture of a liquid and a gas and make sure that it's completely a gas so that we can run it back through our compressor. So that's our closed loop cycle of how a heat pump works. Now I'm going to take the same thing and I'm going to draw it a little bit differently. So we're going to look at it, and as opposed to saying, look, we're taking heat, cold out of the system, we're going to look at it and say we have to add heat in. That's kind of the thermodynamic definition. You either add heat or you take heat out, rather than talking about cold. And so if we look at this, we're going to add heat in into the evaporator. We're going to take hot out of the condenser, and we're going to put electricity into the system. Now, the beauty of a heat pump, what makes these units very efficient, is that we assume that we are only paying for this electricity that's going into the unit. That this heat that we're putting in is going to come from some source that's free. Okay, so if we look at something called the coefficient of performance, and this is just like efficiency of a unit, it's the output that you get, the heat out, divided by the input. And again, the only thing that we're paying for is that electricity in. We have to find a place where this heat is going to come from, okay? The heat, it's going to come from like the air, it's going to come from a source, from a chiller or something where normally it would be wasted. If we have to pay for that heat, say we're taking it out of the air and this is in a conditioned space, if we have to pay for that, then we have to put that into our inputs. And at that point, our coefficient of performance will be less than 1. It'll be 90% or something like that for the cycle. But if that's free, what it's going to look like is we're going to get 3 or 4 or 5 times the amount of thermal energy out versus the electricity that we put into the system. And that's the key thing with these, is that we get more output than we get input. If we just run electricity into a resistance heater, the highest efficiency it can have is 100%. That's just a thermodynamic cycle. So by taking this heat in, we're going to get more out of it. And what it really is doing is taking low-grade heat, let's say it's 50 degrees outside, it's able to take that heat, run it through this cycle, and we're able to get 140-degree hot water out. And that's, of course, something that you could never achieve if you didn't have a heat pump in between. You could only heat it to 50 degrees if that, in regular thermodynamic processes. So really what you're doing is you're taking low-grade heat, you're putting some electricity in, you're getting high-grade heat out, and you're only paying for that electricity. So it looks like it's very efficient. And that's an important thing to consider with these units. Where does this heat input energy come from? How am I going to heat this cycle? And the answer is there's 2 different places that we can do it, or 2 different ways that we do it typically with heat pumps. So we have what's called an air source heat pump, which uses air to heat the evaporator. So these are going to sit outside. People will say, oh, well, let's put them in the mechanical room, and it'll help keep the mechanical room cool because it's hot in there anyways. Well, that's really not a good source because it's probably conditioned space. So if you drop it, if you cool it too much, your heater will have to come on and try to warm that space up. These produce quite a bit of heat. They produce quite a bit of cold as a result. So these have to be mounted outside. And these type of units have a fan coil and a fan for the evaporator. Okay, so that's provided in the unit, and the fans will come on as required when the cycle starts up, when the unit starts up. We also have water source heat pumps, which is another way of saying there's going to be water coming into the unit to heat the evaporator. Where that water comes from can be different sources, but I'll speak some more about that, but it's just wastewater, and now we have a heat exchanger in there as opposed to a fan coil. So those are the 2 different types of units, the air source and the water source heat pump. It just has to do with where the energy is coming from. Now, one key thing about heat pumps, and this is going to vary somewhat depending on where you guys are located, but you have to understand that this cycle can kind of fall apart. So what has to happen is you have to boil off all the fluid in the evaporator. Now, the fluid that's in there, the refrigerant, is just like water. You have a boiling point. If you heat water up on the stove and your burner is only 60 degrees, you're not going to boil that water. And the same thing happens with the refrigerant. So there's a boiling point or a minimum temperature that any of these units are going to operate at. And that means your performance is going to basically fall to zero. If you cannot evaporate that water, if it's too cold, or sorry, if you cannot evaporate the refrigerant, you are going to have an issue. Now, the other thing to consider with these two, and as you can see, is even if you are able to work these things, it's not like a fossil fuel powered unit. It's not like an electric, it's not like a gas, because it depends on the temperature that you're feeding this unit as to how well it performs. So there's not a constant performance. As you can see, the coefficient of performance on this particular unit will get up to be about 5 if the outside air temperature in this case is greater than 80 degrees. If it's less than that, it'll get down to about 3. So how do you size this? The power is dependent on your coefficient of performance. That's this orange line. And you can see this varies between about 280,000 BTUs an hour and 150,000 BTUs per hour. So it depends now on environmental conditions. So they're not the same as sizing a normal water heater. We have to look at all the different cases that are there. On top of that, when you drop below this 35-degree temperature, which is the temperature on our units that is the minimum they'll operate at, the heat pump stops performing, and you need to add an electric resistance heater or some form of backup to it. So therefore, heat pumps, in this case, are a system, and they are not a standalone water heater. Unless any of you are calling from Hawaii or a place like that, where you don't get below this 35-degree point, we have to have some sort of backup. Now, is this a terrible thing? No, it's not actually. And we'll get into some of the reasons why it isn't, but the number one reason is heat pumps are very expensive. If you want to look at a means of heating hot water, heat pumps are going to be the most expensive means of doing so out there. So being able to supplement it at times with a little bit of electricity, you might not save as much money over time, but the initial cost is less as well. So, with some of this variance, what we can do is we can assume that we're going to get the higher output from the units. And then we can use the electric as a little bit of a top up for the system when it's running in times of high demand or something, instead of taking the worst case temperature, the worst case performance, and saying we need to size the system based off of this. So kind of having a mixed system can work very well in many applications. It doesn't have to be a pure heat pump system. And in most of the time, it's not going to be. Yeah, a couple other things. So we have a low temperature package. So if you get below 40 degrees, which is going to be pretty much the continental United States, we put the cold weather package in there. And that's just some resistance heaters in the unit that helps that, in the evaporator that helps the refrigerant evaporate. And then when you get below 35 degrees, a backup system is required. So like San Francisco doesn't get below 35 degrees. Los Angeles, San Diego, some of the coastal areas there. But as soon as you go inland, even a couple miles from those areas, you're going to get below this. And then we need to look at a full backup system. So alternatively, we can look for warmer air in other areas from the building. You can pull from a below ground parking garage if the building has that. And so the idea is the ground temperature is constant throughout the year. So air that comes into the below ground parking garage, it's going to get warmed by that, is going to be above this 35 degrees for the most part, unless you're pulling a heck of a lot of air from a very small parking garage. And you're going to be able to use that. And so that will work even if the air temperatures outside are colder. Now, this has several advantages. So first of all, you have to flow air through a parking garage anyways. And that is something. It takes quite a bit of energy. If you're using the heat pumps for it, you're gaining something from that energy from running that fan effectively. The downside to it is in the summer months when you could be operating more efficiently, you're going to have colder temperatures that you're running through the heat pump. So you're going to get some degradation of performance because even in the summer months, that air is going to be cooler than the outside air. So you can design something where you could duct it or whatever. That would help. But again, you're adding cost and complexity to the system as well. Another thing to consider is buildings with high air changes. You can use the building exhaust. And by doing that, you're guaranteeing yourself a constant temperature of air throughout the year. Instead of just blowing the air outside, you're able to extract some energy from it for the heat pumps. So those are a couple things that you can do to look at air source heat pumps to make them work over a wider temperature range than just the air temperature for where you're designing it for. Yeah, we pretty much talked about the parking garages here. So another type of heat pump that people talk about are ground source heat pumps. And what a ground source heat pump is a water source heat pump that utilizes tubing that's in the ground, again, that's at a constant temperature throughout the year to provide the energy to run the unit. So what you're going to have is there's kind of two ways of doing it. One way is with wells. So you dig straight down and you run your pipe down the well and back up. Or you can, if you have a park, if you're doing a lot of dirt work in a parking lot or something, you can kind of run your tube back and forth, like the picture on the right, below your frost line, then bury that tubing, and then there's a glycol mixture in general that runs through there. So you're going to get stable temperatures throughout the year from this. It's generally not going to be very warm, maybe 45, 50 degrees, really depends on where you are. The other thing to consider is the design of these wells is a very, very specialized thing. So, you know, I'm based in Colorado and our soil is very dry and very clay, high clay content. So we require very long loops in the ground for these to be feasible out here. Whereas I know if you get to some areas like in the Midwest and Nebraska and Iowa, the soil is very moist. So it transfers heat much better, and you can get by with much shorter wells or trenches for these here. So the people that design these are very specialized, and there are engineering firms out there that do just this. A lot of times they're going to be there on site, and they're going to test the dirt as you drill down or in trenches to see what, you know, make sure that you're running enough tubing in the ground. So what'll happen is if you don't run enough tubing, the refrigerant will, or the glycol mixture will freeze the dirt around it. And when that happens, your heat transfer becomes even worse. And then you don't get any output from the unit essentially. So it's imperative that these are designed properly on a job-by-job, site-by-site basis with an engineering firm that really specializes in this sort of thing. So there's also people that use water from groundwater, or you know, there'll be, if you drill down far enough, you get below the water line, you can use water and stuff there. Again, there are options out there for this, and it'll be a very specialized engineering firm that would size that portion. We can provide you with the data and temperatures that we need, how much energy, stuff like that. That's no problem. But you know, we really need to know. We really can't size this for you. It's a real specialized sort of thing. So another thing with heat pumps is we need to start fairly early on in the design process of looking if heat pumps can be used on it. And again, it's similar to making sure there's enough gas at a site that you can use a gas water heater, or you have enough electrical on site. But again, there's a couple things with heat pumps that are a little bit unique. So the first one is we are going to size heat pumps with less power and more storage volume than traditional water heaters. That means they're going to take up more space within a mechanical room. And I should point out, Retrofitting buildings with heat pumps for water heating can be a very difficult task because these design considerations probably weren't there when they built the building. And as you guys know, mechanical rooms are generally quite tight. You don't want to put any more space in than you have to because that costs money as well. All right. So what we typically do, and this ratio varies a little bit depending on applications and sort of other things, other factors that are out there. But if you have a peak load, say an apartment or a dorm or something like that, we size about 600 gallons per 250,000 BTUs an hour of heat pump that we put on the system. Okay, so that's a much higher ratio. 250,000 BTUs in a gas heater, you could have, even 80 gallons of storage or something, right? Almost like an instantaneous sort of thing. And if you have a flat load, something more like a hospital or an office building or something like that, where you don't have these peaks and times when there isn't draw, we go down to about 400 gallons per 250,000 BTUs. Why do we do this? There's a couple reasons. Number one, heat pumps do not want to be short cycled. They want to run for a very long period of time. And giving them the storage where they can run for long periods of time is a very important thing. The second thing is it comes back to the cost equation. It's very expensive for the heat pump, very expensive for the power, and relatively cheap for the storage volume. Now, I know there are some guys here from, say, New York City that are going, hey, wait a minute, our real estate is way more expensive than that. Can you guys go less than this? And in some cases we can. We kind of look at it on a case-by-case basis, how the building's being used, when there's going to be usage and stuff. And sometimes we can. At this point, we're kind of restricting to this 400 gallons per 250,000 BTUs, and going to get some data on the initial systems to make sure that that's a good ratio there. Again, the mechanical room space for all this equipment or space on the roof, if it's an air source that mounts outside. I should mention air sources can mount either inside or outside of a building, depending on whether you want to put duct work in or whatever. But it's, the considerations there, you need to have it from the get-go of the process. The other thing to consider, and this comes into play in residential buildings a lot of times, is you say, oh, great, my heat pump has a coefficient of performance of, say, 4. That means I need 1/4 of the electricity that I need to run a resistance heater for this building. And when it's mandated that you don't produce greenhouse gases on site, that might be an alternative. You say, great, I need to design for less electrical infrastructure. Well, that isn't necessarily the case. So the current draw of a compressor at startup is quite high. It's less than what an electric resistive element would be, but it still is something that you have to design for in these sites. It's higher than you think it would be. So there still is quite a bit of electrical infrastructure that needs to be at a site. The other thing that it requires is some of the smaller units, we can do single phase, 240 single phase. For the majority of these heat pumps, they're going to require 3-phase power. And that may or may not be available within the building or the neighborhood that you're designing for the heat pump. So that's something to look at. A rule of thumb that was told to me years ago is that it's $1 million a mile to build power lines. So again, that could be a very expensive factor. What we're seeing in cities that do heat pumps, Vancouver, British Columbia is probably the best example of this, is that they're requiring that you run 600 volts to apartments. And 5 years ago, they had the same issues. There wasn't 3-phase power anywhere around. And it took time to develop that infrastructure to be able to put these heat pumps in. And I think you're going to see the same thing in many different markets across the United States as these units are rolled out. Initially, it's going to be too cost prohibitive. And you're going to see some people or some cities require this and energy efficiency and stuff, and people will have to find a way to get this infrastructure in place. And then it becomes easier in the future to do it as well. So it's something that takes time to develop rather than as something that's already there at this point. But it is very important to consider from the beginning. And again, this is a thing for a retrofit. It's very hard to say, oh, this building, let's put a heat pump in it because you need the space and you also need the electrical. You might have it, it happens, but for the most part, it's a little bit more difficult to do. So another thing to consider with heat pumps here is they don't adapt to changing conditions very well at all. What do I mean by that? Well, let's look at a chiller. So again, it's the exact same thing. So the chiller has a cooling tower, and the water there has to be cooled, say 10 degrees or whatever. The requirement for most chillers is that you don't change the temperature of that water more than 2 degrees per hour. Okay, so your cooling tower has to adapt to changing conditions and temperature and stuff outside to provide essentially a constant temperature to the chillers. Okay, and then the chiller is going to produce a constant temperature output of the water. Now, let's look at the heat pump. So the very thing that the air conditioner, the chiller, is rejecting, that's what we want. So they're saying 2 degrees per hour is your maximum temperature swing. And we don't always have that luxury. We don't know what temperature we're going to be feeding into the unit. We don't know what temperature the tank is going to be, if it's going to be stirred up, if you're going to get recirc water return, all that stuff in there. So what happens is when there's a quick change in the temperature of the domestic water entering the heat pump, is the pressure within the refrigeration loop can spike, okay? It can adapt to it over time. If you remember, there's an orifice in there, and that orifice will adapt. It'll open and close over time, but it's not designed to move very quickly. So when you change water temperature very quickly, what it has to do is go through a shutdown cycle so that it doesn't blow the seals in the compressor. And so at that point, the unit shuts down. It takes about 6 minutes for it to run a cycle. What will happen is that orifice will open up in the unit, and then it will restart again, and it'll be able to adjust to that temperature. And where that happens is when you're pulling in cold water, and then all of a sudden you get a slug of warm water or hot water into the unit. So we need to design these systems in such a way that this doesn't happen. And so the first thing, and this is becoming pretty much an industry standard, there are some designs out there that are different, is the recirculation losses and the storage losses are best handled with an electric water heater rather than through the heat pump. So this is, again, bringing it down to, we don't have a water heater here. We have a water heating system. And that's a very key distinction between this and other water heaters. We have to look at how we do this, how we provide this energy for these different things. And I'll show you some diagrams here in a minute as to several different ways to do this. But that's a critical thing in ensuring that you have trouble-free performance from these units for a very long time. So another thing that we do with these, and again, this one's kind of becoming an industry standard here as well. There's two ways that you kind of handle the output of the heat pump. So the first is a multi-pass, and this would be typical for how you do it if you had a heat exchanger on the side of your tank, or external water heater feeding it. And essentially what you have is a constant flow through the heat pump. And so it's going to add a certain amount of temperature. In this example, you have a constant 10 gallon per minute flow, and it's going to add 20 degrees. So if you're at 50 degrees, it's going to go up to 70 degrees. If you're at 100 degrees, it's going to go to 120. So that water has to cycle through the heat pump several times in order to come up to temperature. Now, what this can do is produce the exact situation that I just described, where there's a quick change in the temperature of the water. Depending on how well it mixes with each other, with the different temperature water in the tank, it's something that you don't know. What we do, and what most people do in the market now, is we do a single pass. And so we restrict the flow rate of the water going through the heat pump to produce a constant output temperature. So in this example, it's 140 degrees. And as you can see, when you start with 100 degrees, flows 10 gallons per minute, and then that valve closes down at 50 degrees to 4 gallons per minute to give you the same output temperature. And that's a very typical way of doing these. I think most systems specified are this way now, although some people still do specify the multi-pass systems. The single pass is how we're going to help you guys design these as well. I'm going to show you guys some examples here. One of the things is these systems generally have multiple tanks on them. Using the single pass, what we do is we plumb the tanks in series with one another. So if these are 500-gallon tanks, you have 1,500 gallons total storage. We could do a single 1,500-gallon tank. It's quite large, it's quite heavy, it's quite difficult to move around. So oftentimes you want to divide the storage down into smaller amounts. It also can take up less space or fit into a particular space that you may have. So by plumbing them in series, what we then do is the heat pump is going to pull from the bottom of the tank closest to the cold water, and it's going to output to the tank closest to the hot water. So it's going to get the coldest water in the system, and it's going to output right as you're drawing off there. And again, it's going to be a constant 140-degree temperature. Now, what happens is you essentially develop a thermocline within this tank system, where there's a difference between hot and cold water. This happens in your water heater at home. When you take a shower in the morning, you have basically the same temperature of water that comes out of there until it gets cold very quickly. And that's what the thermocline is. The water separates into hot and cold naturally and doesn't necessarily mix unless it's let stand for a very long time. So what we can do now is we can have temperature sensors at different points in the tanks, whether they're high or low, or in the middle tank, or in the leftmost tank here closest to the hot water. We can know how much hot water we have, and we can use those for different things for controlling the system as well. So that's the theory of how this works. All the examples I'm going to show you here are going to show a single tank, but if there's multiple tanks, this is how they're plumbed. So this would be a type of system that we wouldn't want to do. The heat pump here is going to handle everything. So what you have is coming out of your tank there, you have your thermostatic mixing valve, and then the stuff to the left of it there that are the various loops and whatnot for your recirculation loop. Your recirc pump comes back, divides between going back to the cold side of the mixing valve and the bottom of the tank. So that's what the red piping on the left-hand side is. What we're doing here is with the heat pump, we're pulling from the bottom of the tank and we're pushing to the top of the tank. If you're using, say, an external kind of semi-instantaneous heater, this would be the way that you do it. And again, it might loop through that. You might do a 20-degree delta across the heat pump or the heater in most cases. And so it has this kind of multi-pass thing. Again, what's going to happen here is the recirc water could be pulled into the heat pump. You get quick changes of the water temperature there, which we don't want to have happen. And this is going to, just overall not operate to the optimum way that heat pumps can. So I'll show you two systems now and two different approaches. This one is probably the most common one that's out there. It uses what's called a swing tank. Okay, so after the heat pump, which is configured in a single pass configuration now, after the tank or tanks of the heat pump accesses, it goes from that and flows into a backup water heater with an electric element in it. Okay, now, if you have a water source heat pump, you live in Hawaii, you don't need to have any backup electric. This is just going to be sized to make up the recirculation loop. Now keep in mind, recirculation loop losses in buildings can be quite high. So this element may need to be quite large in this tank. Now you say, oh, wait a minute, we're not doing that with a heat pump, therefore we're not operating as efficiently as possible. And that's true. But the heat pumps are really good at one thing in particular, and focusing on that and letting other things like electricity, in this case, that's good at this application, can handle this sort of load pretty easily, handle it, will ensure that the heat pump system will last and perform a longer time. So if the water comes out of the heat pump tank into this tank and needs to be topped off because there's been some losses from standby, which generally are quite low, that element can handle that. That element also handles the recirc losses. There's no way for the recirc return to go into the tank with a heat pump. Now, the disadvantage to this sort of system, well, first of all, there's a couple. So this water heater, the swing tank, cannot be a standard water heater. And I'll give you an example of one system that I just recently saw out in California. So they had 6,000 gallons of storage for the heat pumps, 6,000 gallons, 1,250 gallon tanks. And they had it flowing into an 80-gallon tank that they gave a part number that was a standard off-the-shelf water heater that had 1.5-inch fittings on it. And it was non-ASME rated. So they specified, I think it was 4-inch flange fittings in all these 1,250 gallon tanks that are in the system. And then they have a water heater that's off the shelf at the very end. So you're definitely going to have a pressure drop across there. And I've seen that mistake a couple times. The other thing is, does this tank need to be ASME rated? Well, that's a little bit questionable. It doesn't have an input directly in the tank that's going to be above 200,000 BTUs an hour. So in most cases, so it doesn't need to be because of that. And a lot of times it's going to be less than the 120 gallons. So you don't technically need an ASME rating. However, you have all this pressure in all these other tanks that's pushing on this small tank at the end of your system. And to not make this ASME rated seems a little bit odd to me. It's like an expansion tank for a system like this. It doesn't meet either of those criteria, but most of the time it's going to be specified ASME because there are larger tanks. There are things within the system that are providing the pressure that could be an issue for it. So I would strongly recommend, and when we do these type of systems, that you have this tank be ASME rated and the fittings be designed properly for the flow rates and stuff in the system. Now, the other thing that happens with this is when you need to have a backup system for an air source heat pump. You have no way of accessing the volume in the heat pump tanks. Again, it might be 6,000 gallons of storage that you have in that portion of the system. And this element can only heat the water that's in the swing tank. So either that element has to be quite large or the tank has to be quite large in order to ensure that you have enough power for 100% backup. You've paid all this money for these tanks with the heat pumps, and you might as well use that storage for your backup as well. So this sort of system, you need to design properly for a backup, and it's going to consume more power is what it's going to amount to. Generally going to oversize that element, keep the volume of the tank down. And so it's going to require quite a bit more power infrastructure, which is cost to the system. So these type of systems work. We specify them quite a bit. This is kind of, we'll say it's the established system now that's out there for heat pumps. This is what most people are doing. I'll show you a third way or a second way that we typically want to specify these systems. And this is unique to Hubble and to some of our unique products. So we have the same thing. Now, instead of a swing tank, we have this unit that's called a TXA. And a TXA is an instantaneous water heater. It has a flow meter in it. And the A at the end for us means that it's ASME rated. So now, again, we have our ASME ratings throughout the entire system. And so it's an electric heater. What it can do is modulate from 0% to 100%. So what I can do is take my recirculation return and run it directly through this unit. Now, I'm going to plumb it exactly the same as I plumb the heat pump. So it's going to have the recirc loop come in, and it's going to output to the top of the tank, which is nearest the mixing valve, nearest the output, and it's going to pull from the bottom of the tank, or tank which is closest to the cold water supply. So what I can do is, let's say now it is too cold outside for my heat pump to run. So now this pump below the TXA can come on, And it has the same input as the heat pump. It doesn't really matter what temperature the water is. It's always going to put out 140-degree water. So in this case, it's going to run exactly identical to the heat pump. It's going to pump the water through it. It can access all the volume of the tanks that the heat pumps could. So the size of it can be the same as what your heat pump is, plus whatever you need to make up your recirc losses. So you've minimized now the power draw for your system. And that's the key thing there, because again, all this stuff costs money. All this infrastructure and stuff within the building that you need is a cost factor for these systems. And by minimizing that power, it helps minimize your overall cost, helps maximize the payback to the end user. And that's really what we want to achieve in these. Now, with this, and I won't speak about it a whole lot, we can also do some other things. Having two units that have the same input, whatever temperature water, and the same output, constant 140 degrees, really helps with aspects of designing the systems. So what we could do, we could say, look, let's design the heat pumps for only half the load. We want to save some money. There's only a couple hours during the day, or it could even be minutes, that this electric element is going to run, this TXA is going to run. And we'll just use it to top the tanks off. We have a control system. That's another thing I haven't really spoken about. When you have multiple things in the system that can provide energy, you need a control system that can kind of switch back and forth and understand what needs to go where, when this needs to be enabled, when that needs to be enabled. So, with the controls, then we can kick the TXA on. It can heat the tanks. It can help at the peak load times to minimize the heat pump size. They can work all night to try to come up with a load or whatever we need to do. It offers us more flexibility in the design. So that's all I have prepared here, but I will take questions from anybody who might have them here. Do we make our own heat pumps? We are an OEM manufacturer of heat pumps. What are each of the thermostats doing? Okay. So again, what we can do is some various things. Let's see here if you guys can. This thermostat here, this T1 at the top of the tank, this one is basically used to verify that we're sending out 140-degree water, okay? These aren't shown to scale. I lost my mouse. It's there, apparently. Okay. My apologies, I can't see my mouse right now. So the T1 is kind of a verification there. What we can do is we can use them to activate different things. Again, let's take this example. You want to do you want to have this backup TXA come on, okay? So I can have it come on when the water reaches the level of T2. So there's high demand in the building. There isn't a whole lot of water in the tank. I can run both the TXA and the heat pump when T2 is too cold. We use them for hysteresis in the system as well. It's going to, we can enable on the T2 sensor, the heat pump comes on, and then it disables on the T3 sensor. That would be a typical way that we do it. They'd be closer together than kind of what's shown here. There's multiple tappings in the tank, but just preventing the heat pumps from, coming on and short cycling. A lot of times people would use just the T3 sensor there, and you could have short cycle issues with the heat pumps in that configuration. Yeah, short introduction of the Hubble heat pumps. We have units that range from about 27,000 BTUs an hour up to, in a single unit, about 250,000 BTUs an hour. Again, that's kind of a nominal rating. It's going to depend on the temperature for both air source and water source. And then we have units where we can essentially skid multiple water source units on a single skid to get larger heat pumps. So when you get into larger systems, again, we're going to have more storage than most systems would, but it'll be multiple heat pumps plumbed up with each other, in parallel with each other, and then going to a loop back. So it'd just be in this picture here, the heat pumps would just kind of be stacked to the right of this one with the supply and return coming from the same spot. So that's just as a rundown of the individual units there. Another key thing is we use R134 in our heat pumps. There's different, again, there's different refrigerants out there. We can, if you guys have specific questions about them, let me know. They go down to different temperatures and things like that. So can you add solar to this? If you're speaking of solar thermal, could you? I suppose you could. So my experience is actually with solar thermal, but it becomes very complicated because of the controls on the system and again, the different temperatures and stuff. I suppose you could put something together, and again, the solar thermal, what you may want to do is vary the flow rate through the loop so you get a constant 140-degree temperature out of it or something like that to try to make it easier to control. It's, you know, again, the more systems that you have in here, the more places the energy can come from, the more complex the controls get. And I mean, you could do it, but that's always a worry, I guess, is that the controls just become difficult. It's tough to troubleshoot stuff like that. So, yeah. Domestic water heat exchanger inside the heat pump. Yes. How is that mitigated? If it's an outside mounted heat pump, there's a pump and a heat exchanger in there, and all piping is heat traced. The other thing, of course, is that, you know, it could be mounted inside if you're concerned about that, and ducted outside, depending on where you have space in the building as well. But no, it's the heat trace that keeps it from freezing in most cases. Which is the refrigerants? Again, we offer only 134A. 134A is slightly less of a GWP than R410. They're both still very high, and they will both be replaced January 1st, 2024 by law with another one. And so we will have a new refrigerant in our heat pumps. I don't know what it is at this point, but we will be switching to a different one in order to comply with, I think it's whatever convention it is for them. Any other questions? Oh, are you recommending the backup source be sized for 100% of the recovery? If you have an air source heat pump that is going to be in an environment where it's below 35 degrees, its output at that point will be 0. So yes, the backup system in that case must be sized for 100% recovery. In other cases, if you're in Hawaii and in Northeast climates, yes, absolutely, you would need to size for 100% backup there. Absolutely. Now, there are other refrigerants which go lower, but they give somewhat lower coefficients of performance. And again, if I size my heat pump at the lowest temperature it'll go to, that means I'm going to have a lot more power in my system when it's warmer outside. So heat pumps that go down to lower temperatures, your coefficient of performance might only be 1.5 at those lower temperatures, whereas mine is going to be 3 at those temperatures. It's going to require a lot more heat pumps and a lot more cost if your intention is to run it 100% on the heat pump with, say, an R410, which can go down, it depends on the heat pump, to 15, 20 degrees, something like that. So you would need a lot more size on your heat pump if you do that. So it's kind of a balance of things. Like heat pumps do one thing very well, and then the electric backup is still required on most systems for to ensure that there's always hot water there. So yes, in pretty much all cases in the Northeast, it will be something which is sized for 100% load. Can you put it in the boiler room and take heat from the boiler room? Okay, this is a common question. So the short answer there is no. What happens is we produce a lot of cold air with these units. And so if we put it in the boiler room, it can cool it, but we can't ensure that there is a low enough temperature. If you had a very large boiler room and a very small heat pump, could we do it? Yeah, we could look at doing that. But the boiler room is generally going to be conditioned as well. So the heater will come on if we drop the temperature in there too low. And we don't really want to do that. So there's also codes. I know in California you cannot do that, but I'm not sure about other places, to be honest with you. But most of the time it's going to require the heat pump is pulling in outdoor air or otherwise unconditioned air just because of the amount of cooling that they provide. Yeah. Any other questions here? Oh, have I seen methods of capturing and reusing the cool air? Oh, this is a good question. Okay, so if we just go back to the theory of how these things work, you're going to have a chiller in the building, right? So the chiller is going to produce heat that you're essentially blowing off. Why not use that to heat hot water? Or why don't we use the same refrigerant to run into our cooling loop or cool water with it and run in our cooling loop? The answer is they operate at different temperatures. And the issue that you run into is that a chiller is optimized to chill. So I'm not the biggest expert on chillers, but I believe it's usually 100 degrees to 110 degree water that's coming off of the chiller. And, you know, we need to be able to heat to 140. And the same thing is true with the heat pump. So I don't know the exact chilled water temperature, say it's 35 degrees, we'd be at like 45 degrees or something like that. And if you control one to make it hotter or cooler to allow it to operate with the other one, it's going to make the individual system less efficient. Okay. Now, the other reason that we don't do that with hot water is because there's somewhat intermittent loads. You're not always running your hot water heater or your heat pump or anything like that. And again, for building chiller loops, they want to make sure the temperatures are very tightly controlled. So are there mixed systems out there? Yeah, there are. There are people that mix these and try to utilize them. And if you have, you know, cold air use for it, yeah, you could do it, but it's controlling let me put it another way, it's controlling the output temperature of the water, not the output temperature of the air. And because of our control method there, we can't guarantee you're going to have the right temperature air or we'll say water glycol mixture coming out of the unit so that it will work with the rest of the building. So yeah, that's a very good question. And that's kind of the holy grail of these things is if you can utilize both the hot and the cold that they make, then you're even more efficient. Your coefficient of performance might be like 9, 10, which is great, right? You're able to use everything that this unit provides. It's just the temperatures aren't matching other systems, and optimizing one or controlling one automatically means the other one isn't optimized or isn't controlled. So that's what the difference is. I think in the future, buildings will have to look at means of utilizing this and you know, trying to extract as much energy from sources like this as possible. So maybe in the future, but at this point, no. Anyone else? All right. Well, thank you everyone for your time and attending this event. We really appreciate it. We're always here to answer any questions that you may have. And we'd be happy to help you. It's best if we can kind of get involved early on in the process with the design of the controls and stuff. Thank you, Jason. and just, you know, again, the infrastructure that's required for these systems rather than coming in later on. So thank you, everybody. And if there's anything we can help with, we're always here to help. Thank you.
Thank you everyone for attending. Just so you know, you'll be sent a recording of the presentation if you would like to rewatch or share. And please look out for future webinars we'll be hosting. Thank you again for attending. Have a great day.
Thank you.